So the goal of today's lesson is to be able to solve a logarithmic equation. We've done exponential equations, but now we need to be able to solve logarithmic equations. The steps to do that are to condense the logarithms into a single log using the properties. Now these properties are very similar to our exponent properties and can be summarized in MADSPAM. If you are adding together those logarithms, you're actually going to multiply them in a single argument. If you are subtracting the different logarithms, you're actually going to divide that term in a single logarithm. And if you're multiplying by some constant, you're going to raise it to that power. So if there's a multiplier in front of the logarithm, you're going to raise the argument to that power. It then says that we're going to use the log loop to get rid of the log. Now remember, the log loop is because we have the definition of a logarithm with a base b of y equal to x can be rewritten as b to the x equal to y. There's a loop around of the x and y of the inputs and outputs to get from one to the other called a log loop, going from logarithmic to exponential form. And last but not least, we actually have to check for extraneous solutions on these, similarly to when we checked for extraneous solutions for rational equations, because remember, in a logarithm, the argument, or the stuff in the parentheses, has to be greater than 0. So you're going to take the number we get at the very end and plug it back into the original argument, or arguments, multiple, given from the original arguments, and see if when you plug that number in that the argument remains more than 0. It's not necessarily that the value of x that we get has to be bigger than 0, but that when we plug it back into the argument, that the argument, the stuff in the parentheses, is greater than 0. Okay, again, not necessarily that the value of x is 0, but that the argument is greater than 0. Okay, so if we look at example A here, we only have one logarithm. Great, we don't have to condense anything. So we're going to use the log loop, and the log loop is going to have me do this. So I have 4 raised to the second power equal to the x plus 3. Well, 4 to the second power, that's 16, not 8. Oh my gosh, please don't say 8. That's 16. So I'm really just solving 16 equal to x plus 3, and, well, x is equal to 13. Okay, there's my solution, but I need to make sure that it's not extraneous. So what we're going to do is we're going to check that original argument. We're going to check that x plus 3 is greater than 0 when we plug in our value for x, right there. So is 13 plus 3 greater than 0? Yeah, it is. So we're good. That's not an extraneous solution, and we're done. If we go look at B, B has 2 logarithms. Like you see the letters log written twice, or natural log written twice or 3 times. So we have to condense these together. Remember that if we are adding logarithms together, we can simplify or condense those into a single logarithm if we multiply them. So we're going to keep log with the same base, but inside that argument there, I'm now going to multiply x and x minus 7, okay, because that's what the arguments of these two that I'm adding together are. All of that is going to be equal to 3. So if I just go ahead and multiply that argument together, I'm going to have x squared minus 7x. Okay, I just simplified the argument, distributed the x. At this point, now that I have a single log, I'm going to use the log loop. The log loop tells me that I'm going to have the same base of 2 raised to the third power equal to x squared minus 7x. Well, 2 cubed, that's 8. So really, this is 8 equal to x squared minus 7x. And hopefully your spidey senses are tingling and saying, well, that's a quadratic, so let me set it equal to 0. Let me factor so that I can solve. The number that would multiply to negative 8 and add to negative 7 will be negative 8 and positive 1. And from there, the 0 product property allows me to know that x minus 8 would be equal to 0 and x plus 1 would be equal to 0. such that x is equal to 8 and x is equal to -1. I have my solutions for this logarithmic equation, but I need to double check that neither of them are extraneous. So we're going to go back to the original arguments. There's 2 of them. You have that red argument, I highlighted it red, x, so x is 8. Is 8 greater than 0? Yes. And then I have 8 minus 7. Is 8 minus 7 greater than 0? Yes. Let's plug in the other x. Is -1 greater than 0? No way. So actually, that is an extraneous solution, so we toss it out. It's extraneous. So I only have one real solution here. We have 8. The solution of -1 is extraneous because when we plugged it back in to these original arguments up here, both of them, it didn't work. It has to work in both for it to be an actual solution to the equation. Let's check out C. All right, we've got 3 ln's here. I see 3 times the natural log is written. I need to combine them into 1. To combine them into 1, they all need to be on the same side of the equal sign. So let me go ahead and solve this equation to where all of the natural logs are on the same side of the equation. To do that, I'm just going to subtract the natural log of 2x plus 7 onto the left-hand side of the equation, and it's equal to 0. I now have an addition problem and a subtraction problem, which means I'm going to multiply in the numerator the 2 that are positive and then divide them by the one that's negative when I'm making a single logarithm. This would be the natural logarithm of x times 4x plus 29, all divided by 2x plus 7. I'm condensing it together, equal to 0. Okay, I can simplify that numerator a little bit. I can distribute. This is going to be 4x squared plus 29x, all divided by 2x plus 7, equal to 0. Once I have it to a single logarithm, I can take the log loop. What's the base, though? I don't see a base listed. Remember that natural logarithm is a base of e, so when I log loop this is going to be e to the 0 power, equal to that argument, 4x squared plus 29x divided by 2x plus 7. E to the 0 power, anything to the 0 power is 1, so it's like it's 1. And now I just need to figure out how to solve for x. Well, I need all of the x's out of the denominator, so I'm going to multiply both sides by that denominator of 2x plus 7. And 2x plus 7 times 1 is just 2x plus 7, equal to the numerator 4x squared plus 29x. Hopefully, again, your spidey senses are starting to tingle here because do you see how we have a squared term and some x terms and a constant? We should be like, this is probably going to end up being a quadratic. So let's set it equal to 0 and move those terms to the left-hand side. Nope, that's the right-hand side. I know my lefts and my rights. By subtracting 2x and subtracting 7. And we factor. Now, here's one thing I want to make sure I say out loud. If factoring is not your thing, especially with numbers like 4, 27, and -7, you can always use the quadratic formula to find the solutions. But we're going to set this up for factoring. We should have 4x and x in the front of the parentheses. And I need a number that multiplies to 7, or -7, that would simultaneously add to positive 27. Well, 7 is prime, so the only way to get 7 is 1 times 7. And if I put 1 here and 7 there, it would be 28x and 1x. That's good. I can make 27 out of 28 and 1. That means I need a -1 and a positive 7. And now that we have this factored, we just use the zero product property to solve. The zero product property tells me that x is equal to 1/4 and x is equal to -7. And we think that those are the solutions, but before we're done, because logarithms have some sort of restriction on its domain, on its x's, we have to double check that these are not extraneous. So we're going to go back to the original arguments. The original arguments, there's 3 of them. Let's highlight them in red here. We have x, we have 4x plus 29, and we have 2x plus 7. We've got to check all 3 of them. Okay, so let's check with this first one. We are going to check if 1/4 is greater than 0. Obviously, yes. We're going to check if 4 times 1/4 plus 29 is greater than 0. Also, obviously, yes, because it's all positive. And if 2 times 1/4 plus 7 is greater than 0, again, obviously, yes, all positive. But when we check that second solution here, even in just the first argument, we get -7 greater than 0, and that's not true. So this -7 term is extraneous. We toss it out. Always make sure you're checking those extraneous solutions. All right, we've got the last one here. Question D. I lost it. There it is. Now, we want to condense it into a single log so that we can solve this equation. Right now, I have a subtraction sign. Subtraction means that when I condense these logarithms into one single logarithm, I'm going to divide those 2 arguments. X plus 2 would get divided by x minus 5. Once I have it in a single log, I just use the log loop. Base of 2, exponent of 3, equal to x plus 2 divided by x minus 5. And again, 2 to the 3rd power, that's 8. So really we have the equation 8 equal to x plus 2 divided by x minus 5. If we want to solve both equations for x, I need to get the x's out of the denominator, so I'm going to multiply both sides by x minus 5, which means I'd have 8 times x minus 5. I'll show my work on this one in case you're like, where did it go on? I did this on number C as well. We're multiplying by x minus 5. These will cancel, which is why we multiply by x minus 5. So that I'm only left with, after distributing this 8x minus 40 equal to x plus 2. That's just a quick little linear equation that I can solve, getting all of the x's on the left-hand side and all of the coefficients and constants on the right-hand side. I'm going to subtract x from both sides and add 40 to both sides. Divide by 7, we get x is equal to 6. Now, we think that's it, but remember, we have to check those original arguments. I'm going to highlight these arguments in purple this time. We're going to check all 2 arguments to make sure if we plug in a 6, that we still have a value that's greater than 0. So we want to check and see if 6 plus 2 is greater than 0. Yes, it is. How about 6 minus 5? Is that greater than 0? Yes, it is. So we're good with leaving x equal to 6 as my solution here. It is not extraneous, but we always have to check. Okay, so remember the rules to solve a logarithmic equation: condense all of the logarithms into a single log using all of the exponential properties, logarithmic properties we've talked about, which are just basically the exponent rules. Use that log loop, like when we were evaluating these functions, to get rid of the log and change it back to an exponential equation that we can then find a value of x for. You may have just linear equations left, like a and d, or you may have a quadratic equation like b and c. Either way, you're going to solve for x and then double check that the argument has to be greater than 0, or else the value of x that you got there is extraneous, like you saw in B and C.